let's start. Thanks again, Gustavo.
Just 1 second, I need to put this. Hello, hello. Okay. Are you ready for your next snap? Huh? Okay, good. I need this. Yes, so I can snap you. Yeah. Just to wake you up. Okay, if I remember correctly, oh, sorry, this is not in full screen mode. If I remember correctly, we were with this novae, sorry. This, as you remember, are binary systems formed by a star, a donor star, and then a white dwarf. So a white dwarf essentially is a degenerate state, star, sorry, that is basically dead. But when the accretion proceeds on the surface of the star, it can occur a thermonuclear runaway explosion. And this explosion can generate gamma rays. So I was mentioning that we have two types of these novae, symbiotic binaries and classic novae. The symbiotic ones are systems with a red giant, so the white dwarf moves inside the atmosphere of the red giant, accreting directly from the atmosphere, and then they have these thermonuclear explosions in a recurrent way. For instance, every 20 years, something like that. And classic novae, they produce larger explosions, but not so frequently, let's say. Well, so Fermi detected the first novae, a classical one, B407 Cygnus, in the year 2010. And here you have the spectrum. You see that the emission can reach beyond 10 GeVs. So it's Fermi source, a high energy source, not very high energy source. And then Fermi detected several other of these classical novae. But then it appeared this system, RS of Yuki, is formed by a white dwarf plus a red giant. And it presented a huge outburst in August 2021. And here you have the detection of this outburst in different wavelengths. The most interesting thing is that it was detected at very high energies. First by magic, so the emission was more or less constant during a couple of days. And then at high energies, as detected by Fermi, the emission decayed along several days. And in the optical, there was a slow decay of the radiation. So what happened here? The idea is that we have the white dwarf, this is the red giant, and then the thermonuclear explosion occurs here. There is an ejecta of material from the surface of the white dwarf, and this produces shock. This is not a very fast shock, as in supernova remnants. It's rather a slow shock, but it's plenty of gas, so there is a lot of targets for proton-proton interactions. So these are different fits of the spectral energy distribution for RS of Yuki with Fermi data and also magic data. And on the left, you see a hadronic fit, and on the right, you see the leptonic fit. And this, if you compare these two spectral energy distributions, you will see that in the case of a hadronic case, you need just a single power law to fill the entire cell, with an index of 2.2. But in the case of the leptonic scenario, you need a broken power law. The first part of the power law, below the 16 giga-electron volt, is extremely hard for the particles. It's with an index of 0.5. So this is extremely hard, extremely difficult to achieve. And then at higher energies, above 16 giga-electron volt, then this is extremely steep now. So it's a broken power law that is quite difficult to explain, the origin of this population of particles. Instead, this index is quite natural for Fermi acceleration. So clearly the spectral energy distribution favored the hadronic emission. And if we look at the time evolution, these are the days that go from August 9 to August 12, you see that again, the hadronic model can fit every single day with a single power law. That is a natural power law produced by diffuse shock acceleration. While in the case of the leptonic scenario, we have always a broken power law, but the index in this power law is changing from one fit to the other. So again, this almost rule out the leptonic origin. So people is convinced that we are seeing a hadronic source. And the most interesting point is that, as you see here, the emission reach 1 TeV, and some of the days even a bit more. So by first time, one of these low energetic events, novae, have been detected as very high energy sources. This plot here is shows you the different novae that have been detected so far. So the blue dots are the classical novae, and the stars are the symbiotic novae. And Ras Ophiuchi is right here, so it's the most energetic one detected so far, with a total energy deposition in the interstellar medium of the order of 10 to the 43 erg. That is, of course, almost an order of magnitude less, several order of magnitude less than a supernova remnant, but nevertheless is a significant amount of energy. And this is the fit of the Hess data for this very same object. And you see that the Hess spectrum extends up to 10 TeV. So this shows that probably in this system, protons were accelerated up to 100 TeV. That is a lot. It's not a PeVatron, but this is a very energetic source. And these are two images of the source obtained with Hess. This is 5 days after the explosion, and this is 4 weeks after the explosion. So you see how the source was fainting in meanwhile. Okay, now let me say a few things about microquasars. Microquasars are perhaps among the most interesting objects in the galaxy and maybe in the universe. These are also binary systems where matter is accreted from a star onto a compact object. This compact object could be a black hole or a neutron star with a low magnetic field. Why a low magnetic field? Because if the magnetic field is very strong, then it could stop the accretion at some distance from the compact star, avoiding the production of the basic ingredient of any microquasar, that is the jets. Microquasars are X-ray binaries with jets, and jets are collimated outflows of particles and fields that are moving almost perpendicularly to the accretion plane at very high velocities, relativistic velocities, that could be close to the speed of light. Okay, there are about 25 microquasars known in our galaxy. These are radio images of some of the most famous one. Cygnus X1, ultra-famous X-ray source discovered in the early 70s. Then we have GRS 1915, the famous microquasar close to the galactic center, where a superluminal motion of components was observed by first time. This was one of the covers of Nature that Felix Mirabel shows in every single presentation in the last 20 years. So perhaps you have seen this image before. This superluminal expansion, of course, is not a real effect. Nothing is moving faster than the speed of light. It's just an aberration effect, relativistic aberration effect produced by the projection in the plane of the sky of the components. This is Cygnus X3. Another very interesting object is a black hole orbiting around a Wolf-Rayet star in the Cygnus region. And the period is extremely short, a few hours. So the object is almost moving through the base of the wind of the Wolf-Rayet star. And it presents, as you see, powerful jets. Now we know that this is a super Eddington source. Then we have SS433, the first microquasar identified in our galaxy in the 70s. And this is a very interesting object. The jets are extremely powerful, the most powerful jets in the galaxy, with a power of 10 to the 40 erg per second. And the jets are precessing. So you see here the trace of this precision in the radio image. And this is the Great Annihilator. I mentioned it before. Is located close to the galactic center. Now, there is a variety of microquasars, and there are different proposals as how to classify this object. For instance, low or high mass microquasars, depending on the mass of the donor star, or black hole neutron star microquasars, or high and low spin microquasar. This is a bit tricky because to determine the spin of the compact object is absolutely not an easy task. And then perhaps the most physical classifications are based on the spectral state and the accretion regime, and I will give you these classifications. Yes, of course.
Surprised me a lot in the sense that the signature in the jet of the wobbling of the accretion disk inside the star can propagate to outside.
Mm-hmm. So this was the Marshall talk, if I remember correctly, right?
It was the guy from Gottlieb.
From Gottlieb.
The guy from Flatiron. Yeah.
Yes, actually, if you give me a few minutes, I will have several slides devoted entirely to SS433, so I will mention it that. But first, I would like to introduce some classification in order to know what we are talking about from the point of view of the spectral energy distribution. This is a set of typical spectra from a microquasar. In this case, these are real data from Cygnus X1. This is a canonical high-mass microquasar. So we have the source in different spectral states. There is a state that is called the soft state, that is this one, and it's called the soft because you see that the peak of the emission is at soft X-rays. So in this state, what is going on, we think, is that the accretion disk produced the bulk of the X-ray emission we observed. We observed this emission like this broad peak here. So this soft state corresponds to this state. It's called soft high state because At low energies, the emission is very high. So the accretion disk extends all the way up to the last stable orbit before the black hole and dominates the X-ray emission. In this state, no jet is ever observed. Then we have the hard state that is also called the low hard state. Now the emission at soft X-rays is very low, hence the name, but the emission in hard X-rays is very strong. So actually the peak of the emission is around 150 kilo electron volts and is of more or less of the same order of magnitude than the soft emission in the other state. So in this case, we think we are in a situation like this, where the accretion disk is truncated far away from the black hole, and the inner part, close to the black hole, is surrounded by a very hot plasma that is called the corona. This plasma is so hot, electrons with temperature 10 to the 9 Kelvin, that can comptonize the radiation coming from the accretion disk. And this comptonized radiation appears as this bump that you see here at X-rays. And we have also transitional states from this state to this state. For instance, there is intermediate states. So most of the time the source is in the hard state, and in the hard state a jet is usually observed. So sorry, the source most of the time is here, which have a jet, and then suddenly the source switches to the soft state, and then when this transition occurs, these plasmoids are ejected. These superluminous blobs that are observed in several sources, and then we are in the high soft state where no jets are detected. And then the cycle repeats. So this is a diagram where you have X-ray luminosity that is proportional to accretion rate, and in this axis you have the spectral hardness. So this is the accretion rate in units of the Eddington rate. So you see that in the low state we have a low accretion, and in the high state we have a higher accretion, but always we have sub-Eddington accretion. This disk can be very well described by the classical Sakura-Sunayev thin disk, geometrically thin disk, but optically thick disk. And in this state is corresponds with this truncated disk plus a corona, but also can be interpreted as an advective dominated advection flow. Okay. So if we look at these systems from the point of view of the accretion, we have something like this. This is the accretion rate. At very low accretion, we have a disk that is very thick, is advection dominated, is radiative inefficient, is formed by a gas with very high temperature that comptonize soft photons. And then at higher accretion rates, the standard disk just goes all the way to the black hole, and then this disk is optically thick and geometrically thin. It's the traditional Sakura-Sunayev disk. And then we have the Eddington limit. You know what the Eddington limit is, I guess, is the accretion rate that a system can tolerate before the radiation pressure stops the accretion. But this an ideal regime for spherical geometry, so in several conditions the system can get accretion that is higher than the Eddington limit. If we go to super Eddington regime, then we have this other situation with a hot and dense disk that is both geometrically thick and optically thick. Optically thick means just opaque. Radiation from the interior cannot escape. And a jet can appear also in this configuration, and also a jet appears in this configuration, but never a jet has been observed here. This is related with something that I will mention now. You remember that in the first lecture I mentioned Kerr black holes, and mentioned that Kerr black holes, rotating black holes, have an ergosphere, a region of space-time that co-rotates with the black hole and is located outside the horizon. So let's imagine a situation where we have one of these black holes. The black hole is this sphere here, and this other sphere is the ergosphere. Perhaps the situation is clear here. This is a Kerr black hole has two horizons, the external horizon and the inner horizon. This is the external horizon, this is the inner horizon, and this is the ergosphere. So nothing can be static here as seen from infinite. So let's imagine that we accrete poloidal magnetic field to this black hole, and then the magnetic field enters in the ergosphere, so, sorry, it is twisted. I mentioned this before. And then when you twist the magnetic field, you create a Ponting flux that goes out in the outward direction. Why? Because the magnetic energy density is larger here than here, so you have a net force in the outward direction. So you have dissection of this Ponting flux, as in the animation that was over there. And it's very easy to calculate what is the power ejected by the system through this mechanism. This is a simple version of the ultra-famous Blanford-Naik mechanism. So if you want to know the order of magnitude of the outflow, well, let's just compute what is the magnetic energy density inside the ergosphere. That is B squared divided by 8 pi. And we need to multiply that by the cross-section of the system and the velocity of the outflow. The Ponting flux has a velocity of the speed of light, so we need to multiply by pi c r squared, because the cross-section is p, the gravitational radius to the square. So if we replace these quantities by suitable units, you get this expression that essentially is the Blanford-Naik expression. So it's of the order of 10 to the 35 times the magnetic field in units of 10 to the 6 Gauss to the square, and the mass of the black hole in units of 10 solar masses. And this is the spin of the black hole. If we assume that black hole is maximally rotating, this number is 1. So let's consider a black hole of 10 solar masses, like more or less in Cygnus X1. In Cygnus X1 is 20 solar masses, but this the same order of magnitude. And then the magnetic field could be larger. Let's say could be 10 to the 8. But if you put here 10 to the 8, you have 4 more orders of magnitude, so you get a total power of 10 to the 34 erg per second. That's a lot. And actually the jet of Cygnus X1 is estimated to have a power between 10 to the 37 to 10 to the 38, in good agreement with this very, very simple calculation. Okay. This is the animation I was mentioning before. Okay, so the jet then starts as a magnetically dominated outflow, and somehow matter enters in this magnetically protected region, probably through photon-photon annihilation that creates locally electron-positron pairs, and from neutrons that are produced in the in the RIAF, in this hot corona around the black hole. So there you can produce neutrons from proton-proton interactions there. Neutrons do not see the magnetic field, so can enter to the base of the jet, decay there, and they can inject protons and electrons. The protons can move very fast, and they can produce a lot of electron-proton pairs, but Bethe-Heitler effect. So very soon you will have your original Poynting flux just transformed in a jet with a significant content of particles. But nevertheless, at the beginning, it will be magnetically dominated. And then, since we see radiation, non-thermal radiation from the base of the jet, something should accelerate particles to power law, probably magnetic reconnection in this region. Then, as the jet expands, the magnetization goes down, and then shocks can appear. You know, if you have a magnetization larger than 1, then you are in a magnetically dominated fluid. So this means that the fluid is mechanically incompressible. So you cannot produce shocks. But when the magnetization goes to 1, below 1, then you can compress the fluid and you can generate shocks. So in this outer part, around 100 gravitational radii, you can have shocks and also produce non-thermal distribution of relativistic particles that produce the radiation that we see from the base of the jet. And there are a lot of additional effects. For instance, this is the black hole that is moving around the star. The star could have, I don't know, 40, 50 solar masses. The black hole could have just a few solar masses. So essentially the black hole will move around the star, so there will be Coriolis forces that will bend the jet. So this will produce additional shocks and other effects that can be taken into account. Actually, on long distances, an helical structure for the jet because of the Coriolis force can be produced. And the acceleration and radiation region, yes?
Is there a maximum angle for this bending without disrupting the jet?
It depends on how close the black hole is to the star and the orbital velocity of the black hole, and also what is the rigidity of the magnetic rigidity of the jet. So there are several parameters. In principle, it can be disrupted, but then, since the base continues ejecting, the jet will be formed further away after this disruption.
Because I have the feeling that phenomenologically people abuse bent jets in explaining things.
Yeah, yes, of course. These are not pieces of rubber that you can twist and twist as you want. This is formed by magnetic fields and by particles, so it's a very light fluid, and it's easily to perturb these fluids. Also, there are instabilities that I have not mentioned, Kelvin-Henkel instabilities and other instabilities that can affect the jet. And if we consider that normally, also, phenomenological people use always one-zone model. One-zone model means that everything in your emission region is homogeneous, magnetic field, density, everything. No? But in the real world, things are not like this. The emission region is inhomogeneous, so you need to model an inhomogeneous region that is extended with different densities and different values of the magnetic field. There are different forms to deal with this mathematically, but you can do that, and you can produce very complex spectral energy distributions. For instance, this is an example that we have calculated with some of my former students for Cygnus X1, precisely. And you see that there are many components, sorry. You have synchrotron radiation, you have the accretion disk, you have the Comptonization from the corona, you have a synchrotron proton emission, you have proton-photon, proton-proton, you have proton-proton with the stellar protons of the wind, you have interactions with photons from the disk, from the star. So it's complicated, but you can get this kind of very good fits, and I want to remark that here we are predicting, and this is just from the base of the jet for Cygnus X1, emission beyond 1 PV. So we are saying 10 years ago that Cygnus X1 is a PeVatron. Okay. And there are many other effects that have been studied through the years by people in my group and people in other groups. For instance, if you have a wind from the start, this wind will be not homogeneous, will be clumpy, because we know that the winds in massive stars tend to be clumpy. So these clumps are like small clouds produced by thermal instabilities in the wind. So the situation is more like this. This is from a paper that I published in 2003, long time ago. And when one of these clumps enter in the jet, well, it will produce proton-proton interactions, and you will see a flare. And these are numerical simulations of this situation made by Perucho and Valentivos Ramon. And you see how when the clamps enter in the jet, the fluid is perturbed, and, well, a lot of things occur that produce severe changes in the radiation regime of the source. For instance, Cygnus X1 show a flare some time ago. If I remember correctly, this was in 2010 or something like that. This is from a paper by Roberta Sanin, 2016, but the flare was older. Well, you see that with these clamps, you can reproduce very well the high energy tail of the radiation. And these jets, of course, then after the particles are completely cooled down by radiation, the jet continues moving as a dark jet because it doesn't emit radiation anymore through the interstellar medium until up to they interact with some cloud, with some obstacle, with something in the interstellar medium, and then they produce a bow shock. And in this bow shock, the part of the kinetic energy of the dark jet is transformed again in energy of the particles. This is the bow shock produced by the jet of Cygnus X1. This is the jet of Cygnus X1 as seen in radio, and this is the large-scale emission in radio produced by the impact of the dark jet with the interstellar gas. And this is thermal radiation. But in principle, in all the type of jets, more massive, we can have here non-thermal emission as well. And well, those systems with high spin in the black hole and low accretion rate produce fast light jets because they start as a Poynting-dominated flux, as I have been discussing in the case of Cygnus X1. But there are other type of systems, like the ultra-famous SS433, this object that Ulysses was asking about. This is a super Eddington source. So this means that the accretion rate is huge, and the disk is very hot, is inflated, and the radiation pressure on the surface of the disk is so strong that matter is ejected by the surface of the disk as a wind. So most of the accreting gas is ejected by the accretion disk. It doesn't go into the black hole. Only about 1% of the gas ends in the black hole. The rest of the gas is ejected by radiation pressure. And if in addition we have accretion of magnetic field onto the black hole, we could have a faster spine jet moving inside this wind that is more slow because it's extremely heavy. And in the case of SS433, this heavy dark jet produces a huge perturbation of the interstellar medium. One of these super Eddington microquasars was discovered in other galaxies. It's so powerful that can be seen in other galaxies. It's S26. You will see a poster by Avaroa. No, I think the first author of the poster is Florencia. Yes, in the poster room. and is in a nearby galaxy, and it's called S26. It's a super Eddington source. The size of this microquasar is huge. It's much huge than is huger than the SS433 in our own galaxy. The jet power could reach 10 to the 41 erg per second, so it's extremely powerful. And you see that the morphology resembles that of Faraday Type 2 galaxy, with these two hot spots that can be clearly seen in radio. These are non-thermal hotspots, so clearly electrons are being accelerated in the shocks due to the impact of the dark jet against the interstellar medium in this galaxy. And also you see some diffuse radio emission that forms a kind of cocoon that envelops the entire source. Okay. So this is more or less the situation. We have the super Eddington source here, the jets, we have the hot spots, we have thermal radiation from the forward shock, and we have non-thermal radio emission from the reverse shock. And what we propose is that this is a super PeVatron. If you look at the spectral energy distribution, you see that the energy of the gamma rays goes up to 1 or more PeV. So this means that the particles, in this case protons, that generated this radiation should be at least of 10 PeV. So if one of these things is located in our galaxy, it will be easily detected by LASO and in the future by SWIGO and CTA. Okay. Now I will switch to the next lecture, that is the final one. Don't worry, because it's shorter than this. That was a bit long, because I have to review all types of sources in our galaxy. Now I will focus on the starlets, PeVatrons. So let me find where I have this. Okay. Open recent PeVatrons. I think it's this one. Okay. Okay. Now let's focus on PeVatrons. Let me put this again. That's the easy way. Okay. Now, what is a PeVatron? It's an astrophysical source that in principle is capable to accelerate charged particles up to energies of 10 to the 15 electron volts or more. PeVatrons have been predicted from at least a quarter of a century, so it's not a surprise to find PeVatrons in the galaxy. How a PeVatron manifests itself, how we realize that there are PeVatrons in our galaxy. Well, because in the source, particles accelerated up to those energies can interact with different targets and produce radiations with energies that are at least 100 TeV or more. Super PeVatrons, for instance, can produce radiation with photons with more than 1 PeV. This means that the protons or the electrons have energies of 10 or perhaps 100 PeV. This means far away from the knee of cosmic rays. Okay, but there is a caveat here that the protons can be accelerated without important losses in a variety of sources, and then they can be transported by diffusion or advection from the site where they were produced to another site where they can interact with the target. So it's not so easy to identify the PeVatron. So in this case, we talk about hidden or dark PeVatrons because they are not obvious through gamma ray observations. So in the cosmic ray spectrum, you have seen this plot several times in this school. The knee is around here. This is 10 to the 15. So PeVatrons are located in this area of the cosmic ray spectrum. You notice that this is the Large Hadron Collider. So you are in we are in a region where the physics is well known. So from the point of view of the physics, there is no problem, but we need to solve this extremely inverse problem to understand what is going on in these sources, just detecting a few photons from them. And I borrowed this from Felix Saharonian, and perhaps he showed it in his first talk. This is again the cosmic ray spectrum, and we have here the knee, the cosmic ray knee. In this part of the spectrum, we do not have serious problems understanding where the cosmic rays are being produced. Supernova remnants seems to be the best candidate. They have the energetic. We have seen that they can accelerate particles up to almost 1 PV in some cases. So there is no serious problem here. And then from 100 PV onwards, particles should be extragalactic because it's very difficult to contain these particles in the galaxy with the magnetic fields we have in the galaxy. And then we have here the cutoff, and you remember from Rafael's talks, there are some controversy about the origin of this cutoff because of the composition of the cosmic rays that is not completely clear, but probably is formed at these energies by heavy particles. So there is a lot of discussion around here. So the challenge is in this part of the spectrum where the PeVatrons are located, and it seems that the total power that these PeVatrons should give to the galaxy in order to allow for this spectrum should not be very, very high. It should be between 10 to the 38 up to 10 to the 39, sorry, erg per second. So perhaps just a few PeVatrons can produce the cosmic rays we are observing. Okay. So the first thing we can do in trying to identify potential PeVatrons is to study the HeLAS plot, the HeLAS diagram. You know this diagram. I'm sure that Rafael introduced it in his talks. This is a diagram of the magnetic field versus the size of the source. So the maximum energy in principle that a source can achieve is constrained by the magnitude of the magnetic field and the size of the acceleration region. You cannot accelerate a source beyond what the Larmor radius of the particle is. So essentially we have this relation that can be cast if we think that the acceleration occurs in outflows in terms of the kinetic outflow of the system and the magnetization of the system, and we get this relation for the maximum energy of a PeVatron with a magnetization sigma and a total luminosity Lk in units of 10 to the 39 erg per second. Here this omega is just a geometrical parameter of the order of 1, and beta is the velocity of the outflow in units of c. So this appeared just a couple of weeks ago, this expression in a physical review letter, no, in Astrophysical Journal letter published by Felix, Brian Reville, and Wang. Okay, so we can plot now this diagram. Here I have put the kinetic energy of the outflow, and here the maximum energy. So these are some potential PeVatrons. You see that we have Sagittarius A star, the black hole at the galactic center. Supernova remnants are just at the bottom of the spectrum. The color indicates the magnetization. And you see that here we have several microquasars, and super Eddington microquasars are the most suitable candidates. So we have the crab right here. So the crab seems also to be capable of accelerating particles up to high energies. And here you have a table taken from the paper, the recent paper by Wang and co-workers, where these different parameters are shown explicitly for different type of objects. For instance, these are young stellar clusters. For young stellar clusters, well, we are marginally in the PeVatron regime. Perhaps they can accelerate particles up to 1 PV or 2 PVs, no more than that. Then we have supernova remnants. Well, here dependent of a lot of factors. I will mention some of them in a few minutes. We have the black hole at the galactic center, but this is a so complicated region and we know so little about it that the potential range of for acceleration is huge, so I will not comment about Sagittarius A star. I do not have time now. And then we have X-ray binaries, and you see that X-ray binaries are in outstanding position as potential PeVatrons. So if we, and we have the crab. The crab perhaps can accelerate electrons up to 10 PeV. So these are the main microquasars that in principle seem to be capable of accelerating these particles up to these energies you see here. Remember that sigma is the magnetization, and for microquasar typically value is 0.1. What is an electronic PeVatron? No, not only electrons, but also protons. Also protons, yes. I will show you some examples where protons are the best candidates. So let's start with the supernova remnants. Here the idea is to look at relatively young supernova remnants that are close to molecular clouds, so some suitable target. These are two examples, IC443 and W44, but you see that we can fit very well the high energy part of the spectrum through pion decay, so this is essentially a hadronic source, and in this case we have dominance by relativistic Bremsstrahlung. So this is an electromagnetic source. But you see that these are not PeVatrons because the maximum energy barely reach TeV range. So the best candidate seems to be the youngest supernova remnants. And if we, for a very young supernova remnant, we equate the age of the remnant to the acceleration time scale, neglecting the losses because it's very young, then we get this expression you see here. So depending on the magnetic field, the expansion velocity, and the size, we could have or not a PeVatron. But we need significant magnetic field amplification in order to get the PeV range. So it's possible to get such a magnetic field amplification. Well, there is some hints about that this is possible, and I think this is the most interesting case of them all. This is, once again, the ultra-famous RxJ 1713-39. And what we are seeing here is observations with Chandra satellite in X-rays. And you see that here there are some filaments in X-rays, some condensations of X-ray emissions, so some hot spots. And for instance, in this observation in 2000, you clearly see here the excess of the emission, but in 2005 it completely disappeared. And here you have another case. In 2000 there is nothing. 2005 we see this emission that is produced by synchrotron radiation by very relativistic electrons, and then in 2006, 1 year later, there is nothing at all. So the particles were completely cooled down. So we can equate the time scale for the synchrotron losses with the time scale for the acceleration, and we can, from here, get what is the magnetic field necessary for the source to disappear in just 1 year. And we see that the magnetic field is of the order of 1 milligauss. So this is a direct inference of the magnetic field from X-ray observations. And if you look at this number is 1,000 times higher than the average magnetic field in the interstellar medium, that is of the order of the microgauss. If you consider just the compression by the shock, then the magnetic field should be just a factor of 4 larger. So this means if the magnetic field is typically 2.5 times 10 to the minus 6, it should be 10 to the minus 5, not 10 to the minus 3. So clearly here some kind of amplification occur. How? Well, I think that some instabilities occur that help to amplify the magnetic field. So if the magnetic field is like this, and we come back to our previous equation, we will see that this type of sources can, in principle, when they are young, to produce PV protons or PV electrons, but not multi-PV protons, just PV electrons. Let's see a couple of very young supernova remnants. This is Cassiopeia A, and this is again this source. I hate the name of this source. Let's call it Peter for the rest of the talk. So you see here that the maximum energy that we observe with a gamma ray telescope is 25 TeV. So no way to have PeVatron here. And here we have, okay, higher limit, almost 100 TeV. So this could be that in this source there might be 1 PV electrons, but not beyond that. And this is the source with the magnetic field amplification. So the general idea is that supernova remnants contribute very strongly up to the knee, but poorly beyond the knee. This is a final example, now by LASSO collaboration. So this source was detected at 400 TeV, more respectable energy. So this seems to be a PeVatron. But if you look at the image by LASSO, and then you look at the radio image that indicates the exact location of the remnant, you will see that the gamma ray emission is diffuse, is outside the remnant. What happened here? Probably PV protons were accelerated up to multi-PV energies early in the lifetime of the supernova remnant, but they escape and they diffuse to the surrounding medium. And since in the surrounding medium there is a lot of gas, now we see the PV emission not coming directly from the remnant, but from the surroundings of the remnant. This is an example of how the most energetic cosmic rays can diffuse faster than the less energetic ones, so they can reach larger distances, so you can have a diffuse source around your PeVatron. The PeVatron actually doesn't exist anymore. This remnant right now is unable to accelerate particles up to those energies, but these particles propagate in the interstellar medium and interact and reveal their existence. So they were produced in the past. How long ago? Well, the time it takes from the particle to go from here to here. Okay. And this is another example from LASSO also, paper published a few weeks ago. This is a complex scenario. This is lower energies, 25 TeV, but this is at energies that are suitable for a PeVatron. The gamma ray emission is the yellow spot. As seen by Hawk, I think is this. This is yellow, right? Yeah. Yes. Okay, and here again, this is the gamma ray source at energies above 100 TeV. So this is the potential site where PV protons are interacting with gas. And here there is a molecular cloud, but the supernova remnant is here. So once again, it seems that the most fast, the most energetic cosmic rays left the source long time ago, and now they are interacting with a cloud that is outside. So, yes.
How do you know that? I mean, I don't know how much you know about the physical conditions of the magnetic field in this cloud, but you could also have some quasi-ballistic propagation of the particles at this energy, yes, without too much diffusion.
Well,
so simply hit the targets on the other side.
It depends on the diffusion coefficient. If you have a very low diffusion coefficient around the supernova remnant, because you have a very dense shell of matter, then the diffusion timescale could be longer. So in absence of detailed knowledge of the matter surroundings, it's very difficult to infer the diffusion coefficient and then the diffusion timescale. So I tend to think that in the case of supernova remnant, where you have all this shell that is produced by the ejecta, the more the diffusion timescale for escape is a bit longer than in all the situations. So perhaps this is not a very old supernova remnant, but perhaps this proton escaped 1,000 years ago, and now they are not being produced in the supernova remnant because the LASSO is not seeing them here. The gamma rays associated to them, they come from here. Okay, and this is the spectral energy distribution for this source. So, regarding the general conclusion regarding supernova remnants, these are obviously cosmic ray accelerators. We detect them in synchrotron sources from radio up to TeV gamma, TeV energies. Sorry, up to keV energies, synchrotron X-rays. And then we detect them in gamma rays up to 100 TeV, a bit more. So at most, they can accelerate particles up to 1 PeV or a few PeVs. So they, for sure, are not the primary contributors to the cosmic ray, galactic cosmic rays beyond the knee. So we need to continue looking for. So if just a few words about massive stellar clusters. Here it has been shown, well, these clusters were proposed as gamma ray sources long time ago, in the 80s, by Andrei Bykov and co-workers. In the 90s, there were a lot of work, also in the early 2000s. I myself worked on this with Diego Torres for a while. So it seems that these sources can be GV gamma ray sources, and also they can be TeV gamma ray sources. But what about PeV? Unfortunately, it has been shown recently that multiple acceleration in the different shocks that are inside the stellar cluster is not efficient enough to accelerate particles up to PeV. So the only possibility is to have a supernova explosion in the bubble created by the winds of the stars. So this is a more empty region inside the stellar cluster. So the shock of the supernova remnant can propagate to higher velocities than in the normal interstellar medium, up to, let's say, oops, always the same, up to 30,000 kilometers per second. So in this case, energies of 10 PeV can be obtained. But there are just a few of them detected at high energies, so probably they are not major contributions beyond the knee as well. And then we have the pulsar wind nebula. We have discussed these systems several times along these lectures. This is the famous crab, and here you have some other examples. So here the electrons are injected by the neutron star, and then they are reaccelerated, and at the termination shock of the wind, the relativistic wind produced by the pulsar. And there, energies can reach values of PeV depending on whether the energy losses dominate or not during the propagation of the source. The younger is the source, the lesser will be the effect of the losses. And also it's very important the spin down luminosity of the pulsar, because this is the energy budget you have. But notice that at most the spin down luminosity could be of the order of 10 to the 38 Hz per second. That is the output of the crab. So the total contribution of these systems beyond the knee will be also modest, because remember that we need 10 to the 39 Hz per second. And these are efficient electron accelerators and not proton accelerators, because the pulsar is injecting electron-positron pairs, is not injecting ions. Probably some ions can be accelerated if they are accelerated from the ejecta, through the shock that is formed when the pulsar wind interacts with the ejecta. But, well, also there will be losses, photodisintegration. So essentially, we expect that these sources will contribute with electrons with maximum energies that will be of the order of a few, in the best case, PeV. And then we finally reach again microquasars. And here we do not have any of the previous problems. Remember, the microquasar is formed by the black hole, the donor star, the jets, the accretion disk, the hot corona around the black hole. And, well, these are the typical spectral states that I already mentioned. And this is an example of galactic microquasar in our own galaxy, close to the galactic center. This is an image that we obtained with Josep Martí and co-workers from the University of Jaén using BLBI. And you see that the morphology is very similar to the one I showed you regarding this extragalactic microquasar S26. Looks like a radio galaxy with the cocoon and all that things. So, what are the gamma ray emitting microquasars known so far? Well, first Cygnus X3 was detected by Fermi, by Agile. Sporadic emission, sometimes is detected, sometimes is not. Also is a very fast orbiter around the star with a period of 4.8 hours. The gamma ray emission is modulated by absorption because of this orbital motion. And there are reports during the early 80s that this source was producing extremely high energy gamma rays. At that time, nobody believed that, but now, in the light of LASSO evidence, people are reconsidering those early claims. Then we have Cygnus X1, detected by Fermi, also from time to time. And the emission is correlated with the hard state, as I mentioned. There is also some evidence for orbital modulation, agile detected flares, probably due to the interaction of clamps with the jets, and also MAGIC, they reported an hour-scale flare that was explained by interaction with a clamp. Then there is a controversial claim by Fermi that this microquasar, V404 Cygni, was detected during an active state by Fermi. GRS 1950 was detected apparently during a flaring state by HEGRA, an old Cherenkov telescope array. And then we have SS433 that was detected by almost everything in existence, Fermi, Hess, Hawk, everything, with gamma rays that can go up to 100 TeV, persistent emission coming from both lobes, because this is extended source. And also there is some reports of Fermi emission coming from one of the sides of the source. And then we have this other source, the V4641 Sagittarius, that was detected by Hawk up to 200 TeV. So this is probably a PeVatron. All this is previous to LASSO observations. So now what happened with LASSO? LASSO observed 12 black hole microquasars, and 5 of them were associated with ultra-high energy gamma rays. The detections are this. SS433 was detected as an extended source, so you can differentiate emission from the eastern lobe, emission from the western lobe, and emission from the center of the source. So here you have maps of SS433 for the 3 different regions, from the 3 different regions. And here you have the overall spectrum that extends up to several hundreds of TeV. So clearly we have multi-PeV particles in this source. Then we have also a detection of V4641 Sagittarius. In this case, the detection reaches, I think, let me find it here. Where is it? Here, yeah. Yes, directly in gamma rays, almost 1 PeV. So this means at least 10 PeV. This is almost a super PeVatron for the particles. And then we have GRS 1915 here. So this is the spectrum. It reaches almost 1,000 TeV, 1 PeV. Cygnus X1, that is not so energetic, but also is a PeVatron with energies up to 10 to the 15 for the particles. And then we have this other source, MAXI J1820, and you see the spectrum here. So, probably the most spectacular of all these microquasars is S433. This is a super Eddington microquasar, so it's accreting with an accretion rate that is far larger than the Eddington rate. As I mentioned, the jets are precessing. Probably this is the result of a slave precession of the disk due to the torque by the companion star on the accretion disk that produce the precession of the disk, and this also produce the precession of the outflows. The outflows are a combination of a fast jet, probably launched by the black hole, and the denser wind that is launched by the accretion disk. The jets are very powerful. I mentioned 10 to the 39, 10 to the 40 ergs per second. And during most of their way, the jets are dark. They move with a speed that is 0.26, the speed of light. And they precess with a period of 162 days. And the morphology of the environment is also quite complex. This is the nebula that is called W50, probably is the supernova remnant that was produced when the black hole was formed, but it has an elongated form. Why? Because the jets are in this direction, so the impact of the jets in the shell produce this elongated shape of the entire system. From here to here, you have something like 100 parsecs, so it's a huge system. Okay, and what about from the point of view of the gamma rays? These are the images obtained by Hess. So you see the center, the black hole is here. So you see that the gamma rays come not from for Hess, not from the center, but from the external part of the jet. So there is some kind of rebrightening of the jets at some distance of several parsecs from the central source. What we think is going on, we think that the jet expands until the pressure of the jet, the lateral pressure of the jet equals the pressure of the medium. So then the expansion suddenly stops and a recollimation shock is formed. These accelerate electrons, and these electrons produce synchrotron radiation that creates these gamma ray hotspots that you see here. And this is the composition and different energy ranges of this Hess image. And you see that the morphology changes a bit with the energy. And this is the LASSO observation. Now you see the LASSO also see the two hotspots here, but also there is emission from the center. This emission was predicted by my student Matías Reynoso in 2008. So nothing of this is completely unexpected. Theoreticians were expecting this all the time. But of course, the observational people perhaps is not aware of the previous literature. And here you have some fit of the high energy tail of the LASSO spectrum with a combination of synchrotron and, inverse Compton and also hadronic emission. And well, this is information about the magnetic field for this fit and where is the cutoff and what is the spectral index for the particles. The spectral index is quite hard, so it's an interesting thing. And what about these other two microquasars that are PeVatrons, Cygnus X1, the super famous microquasar, and MAXI? Well, the idea is that since these are point-like sources, nothing is standard like in SS433, the radiation is produced either at the base of the jet, and as in our model from 2015, or in the corona around the black hole. And in the corona, you can have a population of non-relativistic particles accelerated by magnetic reconnection. So these particles, both protons and electrons, will interact with the matter in the corona, producing proton-proton and proton-photon interactions. So this will give you a high energy bump. This is a very recent spectral energy distribution proposed by Kuse and co-workers this year for MAXI, and they propose something similar for Cygnus X1. So you see, this is the accretion disk. This is the Comptonization of the X rays from the disk, and then you have this here this P0 bump that is observed up to energies that are between 10 to the 14 and 10 to the 15 electron volts. And this is exactly the same that was calculated by Maria Victoria del Valle, Gabriela Vila, and myself 15 years ago. So the accretion disk is not included here, just to make easier the cell. But you see the quantization, that this part here. Then we take into account the absorption that was not taken into account here. Most of this radiation is absorbed. And then we have the same bump, and the maximum energy you see is exactly the same as here. So this seems new, but actually 15 years ago, it was already predicted. So if you want to take home a moral from my lectures is this: please know your literature, because when you are working on a subject, perhaps 15, 20 years ago, someone also were working on that subject, and they had some interesting things to say. Okay, and let me finish with a new idea that we are putting forward with Leandro Avaroa and Valentín Ramon. Is the idea of dark PeVatrons and super and microquasar remnants. So in the same way that we have supernova remnants, we could have supernova microquasar remnants. And what is a microquasar remnant? You remember this this configuration with the cocoon, the central source, the jets, and the cocoon is full of cosmic rays. Protons almost do not interact in here. So this protons, this is like a calorimeter for protons, and they are contained by the shell of the cocoon. The diffusion coefficient here could be very low, so the escape time for the particles could be very high. So at some point, microquasar cannot live forever because it's a massive star donating mass to a compact object. So at some point, either the massive star can implode, forming a binary system of black holes, or the accretion can be stopped because some effects on the star, or the system can be disrupted, or the star can simply explode. So when the microquasar is active, we have something like this. But when suddenly the central engine is turned off, then we have nothing here. The jets very quickly disappear, and we are left with this cocoon. And the cocoon is plenty of high energy protons that will diffuse and will illuminate clouds that can be outside the remnant or even inside. So these are calculations of the spectrum when the microquasar is on and when the microquasar is off. And you can see that when it is off, the highest energy of the protons just decreases very slowly because the protons are just diffusing slowly. So perhaps most of the cosmic rays we observe in the galaxy between 1 PV and 100 PV are not being produced by those microquasars that are active today. Perhaps they are produced by one or two microquasars that were active 100,000 years ago. Okay, and this is the evolution of the spectral energy distribution for these systems with time, and how they can illuminate nearby clouds with protons that escape. So you see that they can produce emission up to PV energies. Okay, so my conclusions is that the best candidates to produce cosmic rays beyond the knee in our galaxy are young pulsar wind nebula, especially for electrons, then supernova remnants, but only when they explode inside giant or massive stellar clusters, and then microquasars. Perhaps also the galactic center, but I have not talked about that. Microquasars are capable, for sure, because of LASSO observations, to accelerate particles up to PV energies. And most of the microquasars that we are observing doing this are super Eddington microquasars. Systems like SS433, V4641, Cygnus X3. So these are potential super PeVatrons, but these are short-lived systems, so it would not be surprising to have in the galaxy some microquasar remnants that could be PeVatrons, and they could be behind some of these many unidentified sources detected by LASSO without any kind of counterparts. Okay, that's it. Thank you.
Thanks, Gustavo, and well in time. So, questions?
Thank you again. Can you estimate the number of candidates or the number of these shutdown microquasars in our galaxy?
Well, now we have at least 4 of these super Eddington microquasars active in the galaxy. And the lifetime of these systems should be between 10,000 up to 100,000 years. So this means that if we have now 4 active and the lifetime of dead microquasars, these remnant microquasars, is somehow longer than those that are alive, we should have at least that number and perhaps just a couple more. So perhaps we could have 6 of them in the galaxy, in which case is more than enough to inject 10 to the 39 erg per second in cosmic rays beyond the knee in order to explain the spectrum. So I think it's a promising idea. Yep.
Okay, thank you again for the lecture. I'd like also to congratulate you and Leandro. The Hepro talk was really cool about the dark PeVatrons. And I was just asking a question about the source you call Peter, the RSJ17 something. So you said that the synchrotron variability shows effective magnetic field amplification. I was wondering if maybe you could comment, like, if you have an idea why this amplification happens, if it's like a dynamo process or...
Yeah, there are several proposals. Some instabilities in the magnetic field are the favor at this moment. Tony Bell has been working with Anabel Araudo in those topics, but I have to confess that I do not know the details about these mechanisms because these are plasma instabilities between currents that are formed, I don't know how, in these filaments, and they amplify the field. I can send you some references if you want, but I myself, I do not understand completely this mechanism. I'm sorry.
More questions?
No.
Thank you, Gustavo, for the very complete review. This is very new information for me, so I have a basic question.
Please.
But why is it that we see so many binary systems? So why don't we see systems with more objects together interacting? They're mostly 1 or 2 objects.
Well, LASSO has detected 5 so far, and I mentioned that we know 25 in our galaxy. But remember that the detection of this system depends on the exposition. So LASSO catalog is, if I remember correctly, a catalog with 5 years, right? 5 years of exposition. 4 years. So it's just 4 years. So if you wait perhaps another 5 years, you will detect perhaps most of these systems. But remember that there seems to be some trend to detect super Eddington microquasars, and not all of them are super Eddington. Nevertheless, the detection of Cygnus 61 and MAXI encourage the idea that also systems with black holes that are not super Eddington could be PeVatrons. But we have other microquasars, among those 25, that have a neutron star as a compact object. And we don't know nothing about whether these systems with a neutron star are able to accelerate particles at such energy. Because in the case of the neutron star, things are far more complicated because there is a magnetic field attached to the neutron star, not only the magnetic field of the accretion disk. And this magnetic field could be relatively strong, up to 10 to the 8 in order to produce jets and to have a microquasar, Gauss. But that is, anyway, a very significant magnetic field that can produce catastrophic losses for electrons if these particles are accelerated close to the central source. So there are many uncertainties about this microquasar with the neutron stars. I think there is a lot of work to be done on this type of microquasars, and Lukas Paskiewicz has the assignment to work on this type of systems. So perhaps next time he would tell us something about that.
I would like to ask what kind of physical process allow these microquasars to be super Eddington?
Well, you need a massive star, and then you, let me say all the way around. Normally, when you have a massive star and a compact object, the compact object accretes from the wind of the star. Well, then the accretion rate is not very high, because you are accreting from a moving gas. And the accretion rate goes with the velocity divided by the velocity to the third power, so the accretion rate is not very high. But in some cases where the compact object is very close to the massive star, it accretes directly from overflow of the Roche lobe. And then there is a huge amount of mass that goes directly to the compact object, and then you have one of these sources.
So if there are no other questions, I want to ask one.
Please.
Trying to connect something that Felix said in
Okay.
his very first lecture to what you said, and this has also to do with the things that Rafael talked about. So if you consider the time scales and the lifetimes of the particles and of the sources that can be potentially accelerating the cosmic rays up to the NIM, we cannot exclude that this picture that we have of cosmic rays is actually a local fog. Yes? What we are seeing could be the distribution of cosmic rays dominated by some local, very strong sources, and not necessarily the kind of homogeneous picture of what you'd collect in the galaxy.
Yes, but I think that there is a counter-argument to that, because we can see the diffuse emission all around the galaxy, and we do not see any extreme over-density in the flux of gamma rays from any region. So these PeVatrons, the most energetic protons or particles, escape faster, and they reach nearby gas. So if they are just a concentration in a part of the galaxy, the gas in that part of the galaxy should bright much more than in the rest of part of the galaxy. But you remember the image of the galactic plane. So there is nothing, except in the galactic center, nothing that is completely outstanding. So perhaps, and I cannot be sure, but perhaps these sources are more or less distributed along the galaxy. But of course, it could be the case that we are just in a local bubble. But if history tells us something, is that when we think that we are in a special position in the universe, we are always wrong.
Very good. So with that, thank you very much. And now we have the last coffee break, and then you have the hands-on session. And so let me anticipate the farewell to you to now, so that I'm free to go as well. And you can enjoy your time with Ranieri down in the computer room. So thank you very much for your presence. I think you received an email to give some feedback about the school. It's very important, especially for ICTP, that you answer this. So do that, and I hope you enjoyed. I hope you learned new things, and that you can see your faces again in conferences and other moments of the field. Thank you very much.